This segment is about finding dn, the length of the final distance of the entire space after it is expanded. Now, if this explanation is not clear to you, then I would recommend that you watch the segment, What is HB, or what is the blended Hubble constant? Here we're finding the value for dn. Now, dn, as we can see from the diagram, is d1, the initial distance, plus the expansion of space during TL, the time that light was traveling. So whatever the initial distance was, then for however long light was traveling, how much did space expand? Now, for each megaparsec, this question really amounts to this. 1 megaparsec expands to 1 megaparsec plus x, the amount it expanded. And how much did it expand? Well, the amount it expanded is the Hubble constant, and here is this blended Hubble constant, but forget the b for now. The Hubble constant, which is the expansion of space, times the amount of time that occurred, TL, and since we're looking for an answer in the units of megaparsecs, we have to do two things. We have to convert the Hubble constant from kilometers, which we do, so we divide by the conversion factor, and then we multiply by 1 megaparsec. So this is the amount that the amount of the expansion during this period, TL, for 1 megaparsec. And since this is the amount of the expansion for 1 megaparsec, and we know that originally we had d1 as the number of megaparsecs, then the final formula for dn is dn equals d1 times 1 plus dB times TL over the conversion factor, which gives us this formula. Now, it turns out that this formula is wrong, because this formula does not take into account compounding that occurs. Now, what compounding am I talking about? Okay, here's the compounding. During the time that space is expanding, let's say after a certain amount of time, it's gone from being 1 megaparsec to some longer distance, 1.5 megaparsecs. Now, in the next unit of time, the expansion is going to be of the total new length, 1 plus 0.5 megaparsecs. So the amount of the expanded space also creates an expansion. And in the next unit of time, the new total will all be expanded, and so on, for as long as this expansion is occurring. That's the compounding feature that was described in one of the first segments called the meaning of h, or the meaning of the Hubble constant. So instead of a simple formula like this, we need a compounding formula to give a more accurate formula for dn. So with compounding, things look like this. What's the expansion rate for 1 second? Well, here we had the expansion of 1 megaparsec for a whole bunch of seconds, which was the time of light travel. So this expansion amount here, we're going to simplify that and simply put s in place of TL, where s equals 1 second. So that's the expansion rate for 1 second. H blended times s over the conversion factor. Now we can easily set out a compounding formula. dn equals d1 times 1 plus the Hubble constant blended times s over the conversion factor, all to the power of the number of seconds, TL. This is exactly the same as a compound interest formula, and if you want to refresh on that, again, it was already covered in the segment, what does H mean, or what does the Hubble constant mean?